Hello and welcome to lesson 8.5 on using exponential and logarithmic functions. Today we have a couple of goals. One is to write and solve exponential growth equations and inequalities. The other is to write and solve exponential decay equations. So let's read through this first. Using logarithms to solve exponential growth problems. Exponential functions with base e are frequently used in an alternate form of the exponential growth formula to represent situations involving continuous growth. Okay, so we end up with a continuous exponential growth equation. F of x equals a times e to the kt, where a is the initial value, t is the time in years, and k is a constant representing the rate of continuous growth. The continuous exponential growth equation is often used to represent population growth and is the same as continually compound interest formula. Okay, so they're saying what they're saying there. If you think back to the compound interest formula, the idea was that if you're continually compounding interest, that is a different situation than if you're just getting interest all at once. So let's say there's a bank that will offer you interest at the end of the year, so you'll get all your interest at once, versus a bank that will continually give you interest in infinitesimally small time periods. Well, what they're talking about with population growth, now let's say there's a population that doubles every year. Doubling every year does not mean that on December 31st, everybody in the population has a child, and then December 31st the next year, everybody in the population has a child, right? That's not how population growth works. Everybody's not timing things together. It's that the population doubles over the course of the year, where people are giving birth to new people all throughout the year continuously. And even though this is not really the case, we're kind of assuming in that example that rate at which people are having children is generally steady throughout the year. I don't think that's true, though. I think it's actually kind of tied to the seasons. Regardless, those two equations look very similar. So the continuously compounded interest versus the continuous exponential growth. In both cases, there is some initial amount, like P in our continuous compounded interest formula and A in our continuous exponential growth formula. There's some amount that you get at time t. Here, there's some amount that you get at time t. We have an interest rate, and we have the rate of continuous growth. So they're basically the same thing. We're just not talking about specifically interest here. We're talking about any continuous exponential growth that we want to talk about. I'm going to pop over to a different page. So discrete growth would be kind of what I said before. Like if at the end of the year, something doubles. At the end of the year, something doubles. At the end of the year, it doubles. Continuous growth can get us to the same place at each of these points. So they're not really labeling it. But the idea would be that each of these coordinates, so like after 1 year, we have, one box. After 2 years, we have 2 boxes. After 3 years, we have 4. After 4 years, we have 8. So all of those points, like 4, 8, should be on this graph. It won't be on this exact one because they don't have the right growth rate here. But we could make a continuous growth equation. We could make this e to something x. So in this case, I'll kind of jump to the conclusion. It's going to be e to the 0.6, what is it, 0.69, so 0.7x. E to the 0.7x should have all the same points along it as 2 to the x has. Right, so if you have a discrete function that's going up each time, you can get those same values by writing it in an exponential growth one. Now, there's a couple things to say about that. If we compare those kind of graphs, so for example, if we compare, where was I at? What they're saying here, which I find a little bit misleading actually, is that you need to have it be e to the x in order to get this continuous shape. Well, I mean, if I go to Desmos and I just put in 2 to the x, they don't give me a discrete function, right? They act as if this is a continuous idea where we can say, okay, after the first year, we're at 2. After the second year, we're at 4. After the third year, we're up at 8. But they'll also give you points in between. So you can say after 2.5 years, I expect to be, roughly here at 5.6 or something. So my question when I was looking into how to talk about this lesson was like, why do we need an alternative? Why do we need something else? So like I said, I'll cut to the chase. The alternative version would be e to the 0.7x. Now you can see that these line up almost perfectly. If I do e to the x, they're not the same. These two are not the same. But if I put the right growth factor here, I can change the base of my exponent to e. Now, why would we want to do that? Well, let's remind ourselves what the properties of e are. The most important properties are right here. So this is notation that you're not needing for this class, but I'm just kind of trying to orient us towards the future. This is some calculus notation where this is the derivative, which means the slope of e to the x. So e to the x is my red line. The slope is this blue line. So they're showing the slope at this point. Okay, but this would actually be giving the slope at any point. So this is the derivative for the derivative notation tells you the slope of the line. This is integral notation. This tells you what the area is under the line. Okay, so going back over here, let's say that we had some business and for some period of time, this is like its revenue. So it had maybe $1 million. The next year it made $2 million. The next year it made $4 million. The next year it made $8 million. So it was just doubling its revenue every year. Now, if somebody wanted to ask what was the total amount of revenue made, you'd have to add up 8 and 4 and 2 and 1. If you said, like, what's the total amount of revenue after 4 years, you'd have to add up all of those individual revenues from each year. If somebody said, what was the total revenue between year 2 and year 4, you'd add those up. Now, if you were to ask what is the revenue between, let's go back to our graph of 2 to the x, between like January, January 15th of one year to December 12th of the next year. So you wouldn't be going on whole number intervals here of years. You'd be going from like some little, let me see if I can draw this out. Describing is you'd have some function here and you'd be going and looking for like some area in between. Now, that is not a very easy thing to do in calculus, to find the areas under graphs. What can make it especially easy, though, is if the base of your exponent that you're looking for is e. Because when it is e, this is true. So what is true about bases of e is that the slope will be the same as the value in the graph. So for example, if I have e to the x, so y equals e to the x, and I say I want to know what the slope is at x equals 5. What is the slope right here? Well, the slope of e to the x right there is e to the x. So the slope right there is e to the 5th power. So whatever that gives us. Let's just look real quick. So e to the 5th power. 148. Okay. So the slope here is, if we said, this is a line y equals mx plus b, right? This linear line right here, the slope. Well, the slope of that line is e to the 5th power. Okay, that's our slope at x equals 5. So not only does the original function equal 148 right there, right? Not only is this location x equals 5, y equals 148, the slope at that location is 148. Not only is the slope at that location 148, but the area right here is also 148. Okay, that is not true for any other exponential base. That is the why E is so valuable in mathematics, is because once you get to calculus, it allows you to work with calculus concepts of like this, the rate of change, the slope, the overall accumulation of outputs. So like the area down here, it allows you to work with those in a really simple way where you just say that whatever the value is on the y-axis, that is also the slope and that is also the area underneath. Okay, so it's a tool that allows us to do those things in calculus very well. So if we, for example, have 2 to the x, and we want to write it as e to some power, we don't want a base of 2. We want to say the same thing. We want to use this function. We want to use this expression over here, but we want to write it with a different base. Okay, well, we've talked about change of base in logarithms. You can do change of base with exponents as well. So what I would say, basically want something like this. We're saying that 2 to the x needs to be the same as e to some other exponent. Now it's not going to be x, right? Because 2 and e are not the same number. E is like 2.718, something like that. But we're saying, is there a way to get these two to be the same? Well, before I already showed that there was. So when we have y equals 2x, the blue line, and I say over here, y equals e to the 0.7x, the blue line and my black line overlap. Okay, so if whatever this exponent is, as long as the e exponent is 70% as big, you'll get the same line. Now, where did that 0.7 come from? Well, it came from this. So we'll use our standard techniques here to try to get these exponents down. So what I'm going to do is I'm going to take the natural log on both sides. I'm going to say ln of 2 to the x should equal ln of e to the k. With my log rules, I'm allowed to take this down to the front. So I can say x ln of 2 equals k ln of e. Ln of e on the right side, that is log base e of e. Well, that just equals 1, right? E to the first power is e. So we don't really need that part. Okay, so this ln of e will disappear because it's just a 1. And we'll find that that constant that we needed up there was just the natural log of 2 times whatever our old one was. So if we have 2 to the x, we will need to have e to the ln of 2 multiplied by x. Okay, I just flipped these two around. Ln of 2, if you take that to a calculator, you'll find that that is that 0.69 number. Okay, so effectively, just by using a few simple log steps, we're able to take any kind of exponential expression that we are given and turn it into an equivalent expression with a base that allows us to use some very useful properties down the road. Okay, so that is the direction of what we're doing and why we are doing it. Okay, so back to the questions here. In the next video, we'll take a stab at example number 1 using the continuous exponential growth equation.